Swayam Prabha. Digital India. Educated India.
So in this lecture, I will be talking about a kinetic Monte Carlo approach for a coagulation process. So if you recollect, coagulation is something that we discussed before in the context of the continuous Markov process, where we obtained a rate expression due to diffusion controlled coagulation, and then later on I set up a population balance model or Smolchowski equation, where if the particles are identical to start with, we know how to calculate the number of particles over time, also how to calculate the average size over a period of time. Okay. So that part we have done. So the setting of that problem was very limited in application, because we assumed that all the particles should have identical size, and we assumed that the particles do not interact, they are all like free Brownian particle, and the predictions were only valid for a very short time. But in reality, all these assumptions are broken, because generally particles are not same sized. When you create a dispersion, you basically create particles of over a range of sizes. So there is going to be a polydispersity, there is going to be particles of different sizes. In other words, there is going to be a particle size distribution, and then the particles need not be inert with each other. There could be attractive repulsive interactions, there could be van der Waals interactions, there could be electrostatic interactions, there could be many other kinds of interactions that affects each other's dynamics. And then in terms of time, we are not interested only in the very initial times, but we are also looking at the fate of this dispersion over a very long time. Okay. So in reality, all these are very important, and theoretically solving this problem with all this complexity is very difficult. Okay. But we can reach this problem through kinetic Monte Carlo, where we can build all this extra features to the problem. Okay. So that is what I want to talk about today. So the problem in state kind here is, so we have a solution containing particles. So we say that this volume of this solution is some V. Okay. And then we say that the concentration of the particle, which is number of particle per unit volume, okay, is mentioned, is specified, something like number of particles per meter cube, and then temperature also can be specified. And typically the property of this solution also known, the viscosity of this medium, density, all the things are typically known. And if you look at these particles, you also say that the initial particle size distribution can be, let us say, something like a Gaussian. Okay. So here this is P of n, sorry, P of r versus r, where r is the radius of the particle. So you may have particles undergoing having particular distribution. Okay. So what we are asking is, okay, if I time t equal to 0, I have a solution containing particles having this particular size distribution, and you can also specify more things. For example, you can say what is the nature of interaction between these particles also, if you like. Okay. So this can also be specified, if you like. So the question that we want to ask is that how number of particles and average size vary with time. Okay, so this is a kind of question that we can pose. So I have a starting concentration of C in a volume of V with initial distribution with interparticle interactions defined. What would be the fate of this dispersion? How the number of particles will change because the particle may undergo coagulation. Okay, so that means two particles coming together becoming one. Okay, and then because the number is coming down but the volume is conserved, so the average size will increase. Okay, so what is the nature of this problem? So that's what we want to solve. So what we generally do here is, in experimental case, this volume V can be of the order of milliliters or liters, okay, depending upon the scale. Then the number of particles in the system could be of the order of Avogadro number, maybe 10 power 20 or 20, 21, 23. So we cannot possibly take all the particle in our simulations. We generally do, what we do is, we take a small sample from this particular system, okay, and then we probably deal with 1 lakh particle or maybe 1 million particles. Corresponding to that, there is going to be a sample volume we are going to treat. Okay, so what we are saying is, in the simulation we will take a sample volume. So we say this is Vs, and this Vs is much smaller than the actual system volume V. However, the concentration in the sample volume should be same as the concentration in the original system. So we say that N by V should be equal to Ns by Vs, right? The number of particle per unit volume should be same in the original solution as well as the sample volume that you have taken. Okay, so since this is specified, now we have a free choice of choosing either this or this. Okay, so generally, as I said, because we are going to deal with individual particles and the collision and aggregation, and we have to think about computational overhead, how much time we have to solve this. Okay, so typically, as I said, 1 lakh or 1 million is a good number. So if you say that is about 10 power 5 or 10 power 6, that automatically sets the volume that you need. Okay, so that this has to be constant. So we generally choose Ns of the order of maybe 10 power 4 to 10 power 6, depending upon how good the statistics you want this to be. And then once we know this, we also know that Vs has to be based on, okay, so the sample volume that you are dealing with should conserve the same concentration as before. Okay, so then the next thing is to so what we are saying is, we are mapping this problem into a problem where we have a very small system sample size in which there is ns number of particle in a volume of Vs. Okay, so this volume here is Vs and the number is Ns, and we are assuming whatever is going to happen in this sample volume is actually representative of what is actually happening in the entire volume. So we can make that kind of a prediction. So now we want to think about this process of aggregation in the sample volume as a jump Markov process. And so the way we would think about the state of the system, suppose if I say x of t is my state of the system, this would actually mean mentioning the size of particle R1, R2, R3 all the way up to Rns, isn't it? So my state of the system is basically individually specifying the sizes of all the particles in my system. So here I assume that the initial distribution is given, so particles of different sizes are existing. So that's why I'm giving of all the RNS particle sizes. Suppose if all the particles are identical, you don't have to specify state like this. You can only specify x of t as simply just ns. That is the total number of particle of size Rs. Okay, but here we are talking about a more general case, so we specify the entire state of the system as this. Yes. So we have to we have to sample ns number of particle from this distribution. If you have enough number of particles, the sample that you have from this distribution will be representation of the actual distribution, right. So, I am actually sampling ns particle from this distribution because this is given, okay. So if you have enough number of samples, then you should be able to actually represent the entire distribution. Yeah. Come again? Yeah. So yeah. So basically, I mean, even this distribution is not truly continuous. This is also based on an experimental construct, right. Let us say you have created a dispersion, okay. So you're going to analyze, you're going to analyze this system through some sort of an imaging process or some sort of a characterization process in which you'll have particles. Let's say I'm taking images, okay, transmission electron microscope or scanning electron microscope. You take pictures of this particle. You're going to actually construct the histogram based on that. So this itself is not truly continuous. This is a continuous distribution based on an experimental discrete distribution, okay. So as long as you have this, you should be able to sample enough number of particles, okay. So if you have very small particle, let's say if you have only 10 particles, you may have it may happen that you probably have only particles from this side and not from the other side. That kind of an error can come, but you can actually avoid that mistake by taking a sufficiently large number of particles drawn from this distribution. So the state of the system is given by specifying size or volume, whatever it is, of all the particles in the system. Yeah. Sorry, state would be ns into r. So I can redefine my state variable as this ns because that's the total number of particles to start with, okay, and that's going to vary as a function of time because the coagulation will make the particle number decay. But then you have to worry about when there is a change, you will have n minus 1 particle only. Of those n minus 1, n minus 2 would be of same size, the n minus 1 particle would be a dimer, right. Initially I have ns particle, let us say one coagulation happened. So the total number would come by n minus 1. Out of this n minus 1, n minus 2 would be of the original size, one particle would be a dimer. So that you have to account for, you have to specify that, okay. But in this particular thing, what will happen is, here I have said ns, this only at time t equal to 0. As I go further and further, this ns also will become ns minus 1, ns minus 2 and so on. So even number will actually keep coming down. In other words, we can also say this as simply ns and then sizes of all ns particles, okay. So I can define my state variable as number of particles in the system and all their sizes. This becomes a random variable. To start with, you have ns and then it will become ns minus 1, ns minus 2, etc., and correspondingly their respective sizes also. So now the collision rates so if you recollect the the theory that we talked about in calculating the collision rate. So if I have a population of ith particle with the concentration Ci and jth particle of concentration Cj, the collision rates are going to be given by 4 pi Dij Rij, where Dij is the diffusion constant. So we can write Dij as Di plus Dj, and Rij we wrote as average of Ri plus Rj by 2, right? So that means if I have in the continuum limit, when there is a certain concentration of two species, particle I and particle J type, the total collision rates is basically given by this expression. This we saw before. Now you can substitute this for you can write this in terms of so this Di and Dj, which is basically the diffusion coefficient of particle I and J, is related to Stokes size is related to particle size through Stokes-Einstein equation. So Di is given by Kt by 6 pi mu Ri, and Dj is given by Kt by 6 pi mu Rj. Okay. So where K is the Boltzmann constant, T is temperature, mu is viscosity, and Ri and Rj are the particles radii. And then the collision diameter Rij is nothing but the average of the two species Ri and Rj. So now what we can do is, when we start with, we have specified the sizes of all the ns particle. So now we can think about different possible collisions. Okay. So here this I and j here can mean any combination in this set, 1 with 2, 1 with the 3, 1 with the 4, etc., etc., and then 2 to 3 to 4. So you basically have ns squared, half of ns squared time such collisions. Okay. So you can essentially calculate the collision rate for all the pairs, right? I have ns particles, I can enumerate all the number of collisions. Now each particle has a different radius, so because of this prefactor will also change. So that means for every pair that you choose will have a particular collision rate. Okay. In the theoretical part, we assume this rate to be constant because we assume the particle to be of same size. Now I am actually eliminating all these assumptions. I am giving individual size for each particle, therefore each pair would have a different collision rate, right? So now we can think about setting up a kinetic Monte Carlo algorithm after knowing what is the collision rate for each pair. Okay. So the algorithm goes something as follows. The first thing is to initialize. So you will initialize all the parameters that you need. You will you will inform, you will mention the temperature, the viscosity, Boltzmann constant, all the constants and parameters that you need, you will mention, and apart from that, you will also specify the radius of all the particle populations. Next, you will actually calculate Kij, where I goes from 1 to ns minus 1 and j goes to I to ns, right? So you have because it's a binary collision, so you have two indices. The outer loop goes from 1 to ns minus 1, and the second loop will go from j equal to I to ns minus 1. I go from I to ns minus 1, not from 1 equal to n, because I know how to double count. The collisions are symmetric between 1, 2 and 2, 1 and so on. Okay, so what you will do is you will apply these formulas, and then you will calculate Kij. So suppose if I substitute this here, you will see that Kij 4 pi Kt by, so this factor comes out, Kt by 6 pi mu 1 by Ri plus 1 by Rj into 1 by 2 Ri plus Rj. So I am applying this formula for a chosen I and j. I and j are two discrete particles I am taking, okay, and each particle is an individual particle. So this 4 pi remains as such. For this Dij, I use this formula in which the constant terms are Kt by 6 pi mu. I am taking it out. Then I am left with 1 by Ri plus 1 by Rj times this Rij is the average 1 by 2 of Ri plus Rj. So here in this case we need the concentration of ith species and jth species, but now I am talking about in a discrete case. I am taking individual particle I and j. So I have one particle of I, another particle of j, one particle in the unit volume Vs. Okay, Vs is a sample volume. So now what we can do is pi cancels here, so you have 2 Kt or Kt by 3 mu so you'll have something like this. So this is what you are going to use here. If you like, you can actually combine all these prefactors into some constant, and that you can initialize here itself. So let's say some k naught is defined as Kt by 3 mu Vs square. Okay, that's a prefactor, and this Kij is given as k naught times 2 plus Ra plus Rj plus Rj by Ra. So when I do this looping from I and j, I am taking particle of size Ra and Rj, and I am calculating what is the collision rate for that particular pair, which depends on the respective sizes and some prefactor. Okay. So if you look at this units of this, this would be in terms of per meter cube second. Okay, so this per meter cube basically means in the volume of Vs. Okay, so we like to convert this into number of collisions per unit time. We don't want to do per unit volume, so we can actually define Rij as Kij into Vs. because this expression gives rate in terms of number of collisions per unit volume per unit time. But since I have already chosen a sample volume of Vs, I can find what is the total number of collisions in the volume Vs. So that's what I'm multiplying this by Vs. This is like in chemical reaction, the rate is defined as number of molecules reacting per unit volume per unit time. But if you're interested in how much reaction is happening in a given volume, you would write Ra times V. Okay, so that would be number of molecules reacting per unit time. Like that, here we are talking about number of collisions happening per unit time for a given volume Vs. So that would be this. Okay, so now what you can do is, so you can actually end the loop, end J and end I. So when you do this over, you will have for each pair, you will have the rate constants, and then we'll go to the third step. So there is going to be n square order of collisions, and for each collision we know the rate constant. So I calculate the total rate by summing over all the collision rates, I going from 1 to ns minus 1, j going from I to ns. You got the total rate. Once you have the total rate A, and then you find the next jump time based on this exponential random number. Okay, so this u here is the uniformly distributed random number. So just before here you would call u, generate u, and then you found the next jump time. Okay, so time is chosen. The fourth step is to choosing the pair So now we have to choose out of this n square number of collisions, which pair, which ij pair is going to undergo collisions. Okay, so in that case again we use the same idea like before. We are going to construct a cumulative probability distribution for all the pair 1, 2, 1, 3, 1, 4 all the way, and then we are going to construct a cumulative distribution and then call a random number and then see where this random number lies in the cumulative distribution. Okay, so essentially what we are saying is call a random number u2 So here I will pictorially describe what this equation means. This basically a search. What we are doing is I am looking at all possible collisions here. Okay, so I have half of ns squared. Yeah. Here. Here. Yeah. Here. This one should be I plus 1. Yeah. Right. Yeah. 1 2. That should be fine, because when this goes to ns minus 1, this will become ns. So that should be here also. Yeah. So what we are saying is, so here on the x-axis, I am enumerating all the collision possibilities: 1 3, 1 2, 1 3, up to 1s, then 2 3, 2 4, all the way up to 2ns, and then the last pair would be ns minus 1 and ns. Okay, so for each of these pair, I have calculated the rate aij. So based on this, now what I need to do is also to define Pij, which is aij by a, because a is a total rate. Okay, I can now find the probability for each collision as the rate of collision of aij by the total rate of collision. So this will be the fraction, or we can assume this is a probability of occurring this particular collision. So here I am summing all the Pij's. Okay, so this will add up to 1, from 0 to 1. So now I am updating the time for one collision. Now I know which collision is going to happen, which pair of collision is going to happen. Okay, so for that I am going to call a random number uniformly distributed in the limit 0 to 1, and then compare that with the cumulative distribution. Okay, for example, if my random number comes somewhere here, and I have to check for which cumulative distribution this pair corresponds to. So I would actually use 2 comma 3 here. Okay, and this statement is what actually I have written here in mathematical terms, that I am actually summing over all the pairs from I equal to 1 to ns minus 1, j going from I plus 1 to some L, some intermediate L, such that the cumulative distribution up to that pair IL, and the random number actually falls between that pair IL and I and L plus 1, the other ones. Okay, so this basically allows you to do the searching algorithm that we are talking about here. So then once you screen this particular expression, you will find a pair I and L, and those are the colliding pairs. Okay, so now we have to update the system's behavior. So step 5. So what are the things we need to update? We need to update the time, and because this collision is happening between I and L, so we say that the particle size Ri, right, is given as okay, the volume has to be conserved due to the collision. So we update that the new particle, ith particle's radius cube, is going to be sum of the old particle is cube and then L cube, and then update also the number of particles from ns to ns minus 1. So now particle has decreased by 1, factor of 1. Okay, and you may have to update your particle array. Okay, suppose this L happens to be somewhere in between, you're going to just remove that particle and then reassign the index for, if suppose if you are storing this particle information in an array, once an intermediate particle is actually lost due to this collision, you have to update the array index so that the total array now becomes ns minus 1. Okay, so that's something you have to deal with it when you do the coding of this particular algorithm. Okay, so well, we have done that. So after this, after step 5, time is updated, particle size is updated, number is also updated. Okay, after step 5, you will go to step 2 again in a looping fashion. When you come here, now you see this ns has become 1 less from the previous step. Okay, because we are doing a event driven MC simulation. So at every event, one collision is happening. So for sure that you have chosen a time such a way that one collision has happened. So this will decrease by 1, so that you will have when you calculate these ones, you will have ns minus 1 pair less now, okay, from the previous one. And then you're going to do the same thing, sum over this, calculate the probabilities, again find this. In the second step, you will find another pair I and L, and you will update this, decrease ns by 1, and this will keep looping over and over until you reach a particular target time, and then you basically have all the information you need. As a function of time, you have number of particles, and you also know what is the particle sizes in that array, and you can do all statistical estimates, average sizes, standard deviation, whatever you like. Okay, now this is a very basic algorithm, and you will see this is very computationally expensive, because every time you want to execute one collision, you have to search through this. Remember I said ns can be of the order of 10 power 5, 10 power 6, so you have a good distribution. And then the search algorithm requires ns squared number of searches, so that's going to be a lot of computational overhead. Okay, so now there are a lot of strategies to actually avoid this. So you don't do this at every step. There are several updates that I don't want to talk about this later, talk about this at this point. But then if you look at the references that I'm going to provide or papers I'm going to provide, you will see a lot of improvements here. Just one more. The other thing that might happen is, when you conduct the simulation, let's say you have started with the 1 lakh particles. When you do this, let's say when you do 10,000 number of collision steps, the total number is coming down from 1 lakh to 90,000 and so on. So when you go towards the end of the simulation, you have fewer particles to sample from. Okay, so your statistical quantities will have a larger error when you go to larger and larger time. For that also there are some strategies. Okay, for example, that strategy is, for example, whenever you have, let's say you have the first collision happening, one particle is lost. Even at this step, you can copy one particle from the rest of the ns minus 1 and replace the one that is lost, so that the number is always conserved. So such simulations are called constant number simulations. So anytime a particle is lost, you copy one of the remaining one for the last one. This is one way. The other way is, you don't do it at every time step. You wait until this particle drops by 50%, let's say. Okay, so you start with 1 million particle, okay, and let's say you have 5 lakh particle after a certain time. And then at this point of time, you basically double the system. So you basically copy the same, you make a copies of the same particle twice. Again you have, so you can actually increase the number of particle at intermediate steps also. Okay, so this again, the accuracy and computational efficiency, this all has to be discussed in each of this algorithm. Okay, so these are all some handy approaches to make sure your statistics does not become bad when you go to larger and larger simulation types. Okay, so like I said, there's a whole lot of algorithms, whole lot of improvements, computational saving strategies and so on. So, but the basic algorithm remains the same, that you're going to talk about this, you know, this calculation step has to happen. A lot of savings is possible in this step, and then how do you manage your number not going down too much? Okay, so a lot of approaches are possible. Yeah. Here, right? You will do n square calculation time t equal to 0, right? Let's say the first collision has happened. That would have affected only 2 particles property. The rest of them would not have changed, right? Yeah, yeah, that's what I'm saying. I mean, that is always there. What I was trying to say is that you don't have to do this n square calculation all the time. There is also possibility of saving time here, because first time you will do n square calculations. Next time when there is one collision happens, that is only affecting the property of only one particle. The remaining particles property have not changed. So therefore, their collision property also is not changed. So essentially, you are going to only recalculate ns number of new collisions, right? So let's say, give me this way. So let's say I have 10 particles. So let's say in one collision, the 9th and 10th particles are coagulated. Okay. So then from 1 to 8, those set have not changed their sizes. The 9 and 10 has become now 9 with a new size. Now only this 9th particle's collision with all the other 8 particles has changed. I have to only calculate that. I don't have to recalculate 1, 2, 1, 3, 1, 4 because those have not changed. I can store them. I can bookkeep them. So if you have sufficient memory, you can actually keep that list of calculations bookkept. Whenever a particle changes its sizes, update the collision of that particle with the rest only, and there is a lot of computational saving there. So you don't do n square term anymore, you will do only ns. First time you will have to do. Yeah. Like I said, that what is the number that you want to choose purely depends on your statistical estimate accuracy that you want and how much computational power you have. Okay. In papers, when you see when people apply this kind of algorithm, they do 10,000, sometime 1 lakh, because what I have given here is a very simple algorithm. Sometimes if you want to include the interparticle interactions, let's say, okay, let's say the particles are interacting through some electrostatic interaction, that has an additional calculation here. Okay, there's going to be a weightage factor that goes in here, that every step for every pair you have to include that also. So when you add more and more complexity, you have to deal with a very smaller and smaller n. When you use a smaller and smaller n, then you have to deal with how to manage this decrease also. Okay, like I said, there's a plethora of techniques and strategies to manage computational time, right? But the point I'm trying to make here is that you don't have to make any assumption here. You can deal with the polydisperse system, you can deal with the multi-component system, you can deal with the particle-particle interaction whatsoever. Okay, there's no limitation. Okay, but everything is going to come at the cost of computational time. Are you willing to pay for the price? Computational price, right? All right. Okay, so that's it I have to say. So by the way, this is our last class. So we don't have class on Friday, and then I think the last class is 2nd May, I think, right? Last instructions day. So I'm traveling, so I'm not here on Friday. So this is my last class. So thanks for taking the course, and I hope you enjoyed learning some new simulation methodologies, which is very different from any other chemical engineering course. And I look forward to your feedback in TCF. Please do fill the TCF. Thanks.